Hey everybody, today we're going to learn Similarity 5. It's the last lesson of the unit. In order for you to understand what's going on, I'm going to have you draw a little diagram here, and we're going to use the triangle that I gave you. And when we talk about the first theorem of the day, the Side-Splitter Theorem, I actually want you to take that diagram and I want you to split the sides. There you go. I actually want you to draw that. Now, in this case, we are dealing with two parallel lines. And in order to make this work, I think what we're going to do is we're going to take our triangle, we're going to name our triangle ABC, and then we're just going to add our side splitter right here, DE. All right, now, the significance of this theorem is that we end up getting proportions out of it that match up perfectly. If a line is parallel to one side of a triangle, which we just drew those arrows there. I'll make them darker so you can see what I mean. What we just created here, we created DE, which is going to be parallel to that side BC down here. They're not congruent, but they are parallel. If a line is parallel to one side of a triangle and it intersects the other two, then it divides the sides proportionally. All right, so what that means, it divides the sides proportionally. It means that if you did AD and compared it to AE, okay, so if you looked here and then you looked here and you compared them with a proportion, well, with a ratio, we could create a proportion using the other two. And the other two would be DB and EC. Okay, so that's what it would look like. This over this equals this over this. We have created a proportion. And that is going to be very useful when we start getting into some of these practice problems that involve a side splitter. Now, I didn't draw it, but you can just assume that these are parallel for these examples because that's the only way it's going to work. So let's do a couple of examples that look like that. Let's do a 10 and a 2, and then a 15 and an X. Okay, so if we practice this method of just setting up a proportion with the whole thing, we could get 10 over 15 equals, and then we're just going to do 2 over X, and that's it. So you don't have to overthink it. You don't have to do anything extra. You just have to go through, and whatever method you do from here, if you cross multiply, if that's you, that's fine. 10 times X is going to be 10X. 15 times 2 is going to be 30, so X equals 3. If this method seems easy, maybe it is. Let's try another one here, and we'll put like a 2 over here. We'll make that 5. We'll throw in a decimal just to scare people. Not that it's really going to be scary, but whatever. And we're going to put X right there. So the same method that we just talked about, 2 over X equals, and then we're going to do 5 over 7.5. Set it up, take your 4 numbers, make a proportion. 5 times X is 5X. 2 times 7.5 is 15. And so once again, I didn't mean to do it that way, but I guess it worked out. X equals 3. All right, I think we need to get a little bit meaner. Those two seemed pretty obvious. I think we can handle it. We're going to put an x here, and we're going to put an x plus 3 here. And then we're going to go with a 5 and 8.75. That sounds good to me. Now, it is going to work. It is not going to be as awful looking as you think it's going to be. It is turned on its side, but the same idea is going to hold true. So x plus 3 over 8.75 equals x over 5. Same idea. All right, now if you cross multiply, 8.75 times x is 8.75x. If we cross multiply on the other side, if that's what you're doing, remember that 5 is going to need to get distributed here. So what you're actually going to have is 5x plus 15. Now at that point, I think you know your algebra pretty well by now, so we are going to just subtract 5x from both sides. That part of it won't be bad. Okay, and when you're all said and done, you're going to get, and I'm kind of running out of room, so I'll just move it over here, 3.75x equals 15. If you divide, you might not be able to do that in your head, but it does work out just fine. X equals 4. All right, now before we move on, I do have to warn you about something. There is a type of problem that this does not work for, and so I want to be very clear with you. We're going to take our first example, and I'm just going to change it very, very slightly just to see if you can pick up on the issue. Okay. So here, we're going to take our first example, and you can just sketch this on the side of your paper on the margin or something like that. Here we go. We've got that. Okay. So this looks exactly like the first example that we did. The only difference is instead of going from side to side, like instead of going here and then going here, I went through the middle instead. The side-splitter theorem does not work in this situation. Okay, so if you ever get a situation that's set up like this, you are not allowed to do 10 over 15 equals 2 over x. I know it's tempting. Everybody tries to set it up that way, and I continue to yell. Here's the problem. The side-splitter theorem only works when you go from one side to the other. It does not work when you're going from one side to the middle. Whenever you get a problem like this, what you actually have to do instead, whether you like it or not, and this is going to happen at some point, so you need to be ready. We can't talk about everything that we're going to do every single time. What you have to do instead is you have to break it up into two separate triangles and then put the left side together. So instead of calling this 10 and 2, you're going to rename this as the whole thing, which would be 12. So in this case, instead, you would do 10 over 12 equals 15 over x. And so from there, you would get 10x equals 180, which means x equals 18. So again, that was not on your paper, and I get that it was not on your paper. I just made it up. But I'm trying to give you an example of when the side splitter does not work. So again, we've got 3 examples where the side splitter works. Those are all perfectly good examples. I wouldn't do any of them differently. But then if you're not dealing with a side, if you're dealing with one side and then the bottom instead of going side to side, that method does not work. Now, the good news is we can actually apply what we just talked about into other situations involving parallel lines. So the next 2 examples are actually what you would use the side splitter corollary for. Basically, what we're doing is we're taking the concept of the side splitter and we're using it in a different situation with 3 parallel lines. If 3 parallel lines intersect 2 transversals. Now, don't get too caught up in the language here. 1, 2, 3 parallel lines, and then a transversal is a line that cuts through it. So there's one line cutting through it, there's another line cutting through it. So that's what the translation is. Please don't get too caught up on that. If that happens, the segments intercepted are proportional. So basically the same method that we just used, we can use now, even though the situation is different. So let's say we had a 12, and then this one, I'll try to make it a little bit complicated, maybe not that complicated. X plus 1. Okay, and then we'll put an X right there. Then we'll do a decimal just to be a little more annoying. But again, I mean, there's not a lot to this. Okay. If you were to set up the proportion, it would look like this. 12 over X plus 1. So again, as long as we're going side to side and we're not using the middle, this rule works. Equals 10.5 over X. So when you distribute, you're going to get 12 times X, which is 12X. We have to distribute this one, the other part with the decimal. We're going to have to distribute that. We're going to run out of room, so I'm just going to make this a different color, and I'm going to go over the top, and I think you can probably live with that. Let's see. Let's make it bright red. There you go. That didn't come out great, but we'll be fine. If we subtract from both sides, you're going to get 1.5x equals 10.5, and then you will divide. I know the last 2 steps I'm kind of going quickly through, but I think you know how to solve equations. You subtract from both sides, and then you divide. X equals 7. All right, let's do one that doesn't come out pretty, maybe one that comes out to a decimal or something. So we're going to use X plus 1 here. We'll use 12 there. And then we'll go 8. And we will go 10. Now, once again, since we're going side to side and not using the middle, side to side and not using the middle, since we're doing that, what we are doing is allowed. So we're going to follow through and we're going to get it done. X plus 1 over 8 equals 12 over 10. All right, let's see what we come up with here. So that's going to give us X times 10 is 10x, but we have to distribute. So 10x plus 10 equals 96. Then if you were to subtract 10 from both sides, again, this part I will go very quickly through because I think you already know what you're doing. What you end up doing, and you get I'm out of room here, but that's okay. 10x equals 86. So x equals, and it turns out to be a decimal, did not come out pretty, 8.6. All the people who are working ahead get mad and they're like, well, I thought I did it wrong because it came out to a decimal. It's like, no, I'm pretty sure that's just fine. All right, now I want to propose something here. The last example, and this is actually the last example of the entire unit because this is the last note sheet of the unit. I want to throw this out there because a lot of people, you haven't seen a problem like this, and a lot of people might just kind of freeze up. But I just want you to think to yourself, is it possible that the same thing that we just did could be applied to angles? What would happen if we had 2 figures and the angles on each side of this were the same? would you be able to use that same sort of concept where you just made a proportion and you just did 7 over 14? Turns out you can. So even though this problem does not look familiar, you know how to do it. You just don't know that you know, which is always kind of a wacky thing to say. You know, you just don't know that you know. If you distribute, you're going to get 14, or if you cross multiply, you'll distribute on the other side. 14x equals 7x plus 70. So once again, we're going to do the same 2 steps that we've been doing all over the place. We are going to subtract and we are going to divide. We are just about out of room. I hate to keep bouncing around the paper, but we're going to do what we have to do to get the job done. 7x equals 70, which means if we divide it by 7, x is going to equal 10. Now, you probably should know what that thing is called and what it means, so that is the last thing that we're going to write. It's the Triangle Angle Bisector Theorem. Remember, an angle bisector is when you draw a line and that line cuts the angle into 2 equal pieces, and that's what happened here. If you take a look at this line right here, this little segment, it cuts that angle into 2 equal pieces. All right, so the rule officially says if a ray, in this case it was a segment, the same idea, bisects an angle, it divides the opposite side into 2, and the segments that it creates, the 2 segments, will be proportional to the other 2 sides. So when you use the angle bisector and you take this segment and cut it into 2 pieces, they will be proportional to these 2. Okay, so that's the way it breaks down. You can pause the video if you need to write that down. Otherwise, that's all I have for you. Thanks a lot for watching, and I'll see you next time.